Hello and welcome to Real-Time Signals Technologies. Today we are going to discuss about real-time operating systems overview. Topics included: what is RTOS? What is difference between RTOS and GPOS? What is kernel, monolithic versus microkernel, task and TCB, process, thread, scheduling, context switching, stack, state, practical problems and solution, priority, inversion, deadlock. IPC, ITC, intertask communication, message queue, semaphore, mutual exclusion, event flag. A real-time system is a time-bound system which has well-defined timing constraints, means RTOS is used for time-critical applications, mostly used in embedded systems. Let's understand real-time systems with a real-world example. If a driver meets an accident, the airbag will be deployed at the right time and the life of the driver will be saved. But if the airbag deployed after few seconds, the case would have been different. The time taken by the system to respond to an input is called response time, which must be very less and deterministic in case of our airbag example. Real-time operating systems can be classified into three categories. Hard real-time system, strictly follow the deadline associated with this task. Missing on a deadline can have catastrophic outcome, as our example. Firm real-time system, infrequent deadline misses are tolerable, but may degrade the system quality. Soft real-time, in these type of systems missing a deadline is acceptable. Online databases. Some of the most widely used RTOS are QNX, RTLINUX, VXWORKS, FreeRTOS, THREADX, etc. The reason RTOS is preferred as embedded system OS cause with it we can do multitasking. It has predictable behavior and also has very less memory footprint, means it takes very less space in memory. Compare few aspects of RTOS and GPOS. RTOS should have a preemptive kernel for better performance, though you can choose between preemptive or non-preemptive in the configurations. General-purpose operating system may have preemptive or non-preemptive kernel according to situation. Priority-based scheduling is used in RTOS, whereas you can choose between what kind of scheduling you want in GPOS while compiling. Round-robin, priority-based. The footprint of RTOS is very less compared to GPOS. RTOS takes space in main memory in the range of KBs, whereas GPOSs are bulky and can take 1,000 times more space than RTOS. RTOS does not need memory management unit, whereas GPOS's memory management is complex, so a MMU is required. Now, what is a kernel? Kernel is the core of an operating system which is responsible for scheduling and maintaining operating system resources. If we broadly classify, there are two types of kernel: monolithic kernel and microkernel. How do we differentiate between these two types of kernel? Monolithic kernel will have all the subsystems, like process management, I/O and device management, inter-process communication, etc., in the kernel space. Example, Linux kernel, BSD kernel. Whereas microkernels have only few of the subsystems in kernel space. Other subsystems reside in user space only. IPC, I/O management, etc. resides in kernel space. Device drivers, file system, etc. resides in user space. Mac OS X, Windows NT. For security reasons, memory is divided into two parts: user space and kernel space. To access the kernel space memory by user space process, special permission is required, whereas kernel can access any memory without any hindrance. The basic services provided by RTOS kernel to the application software: task management, inter-task communication, dynamic memory allocation services, device I/O. Task is a piece of code which is executed by the kernel based on its state or priority. In task management, the kernel keeps track of the state of each task and the priority of the task, and the scheduler schedules tasks accordingly. We need to divide our program into different tasks to achieve parallel execution of different pieces of code. While a task is running, it stores data that are required for its execution in a memory location which is called the stack of that task. Each task will get its own stack. The task can use that memory until it is running. When a subroutine method function is called, a stack frame is stored on top of stack. It stores the local variables of the called subroutine. When the subroutine returns, the stack frame is deleted. Task states. When the task is created, it will be in ready state, ready but not running. When a context switch happens, the ready state task goes to execution state. If the task is waiting for any event to occur, the state of the task will change to suspended state. When the required event occurs, it will go to ready state, and then to execution state, and eventually to completed or terminated state. Context switching is the process of saving the state of currently running task into the stack and also push the values of CPU registers, variables and program counter to the stack. It is done when an interrupt is called or when a higher priority task is ready to run. A system resource is any usable part of a computer system that can be controlled and assigned by the operating system, so that all of the hardware and software on the computer can work together as designed. System memory, CPU, other hardware associated to the system. These are some of the resources that has to be managed by the real-time operating system. Task management services of RTOS helps create separate tasks for one program with distinct real-time deadline. Services offered under the task management category include the ability to launch different tasks and assign their priority levels. The main services under the real-time operating system are task scheduling when the embedded system is under operation. The scheduler controls application software tasks and runs them in a timely and responsive manner. The RTOS kernel exposes different system calls to create, delete, or schedule tasks. Different priorities can be set for different tasks. Their priorities can also be changed by using RTOS kernel exposed APIs. Xtask create function is used to create a separate task which can have different code section. We can set how much memory the task will take in the RTOS heap by setting a value for a stack depth variable. We can also set different priority, pass different parameters to the task code. Last parameter PC created task pointer is used to create and store a handle for a particular task. The delete, suspend, and resume functions can use the handle created in the task create function for deleting, suspending, or resuming a task. In RTOS, higher the value, higher the priority. The highest priority value can be changed using a hash-defined macro in RTOS config h file. As this value is architecture specific, so it is not recommended to change the value directly. We should use the default value. But if we want to change the priority of a particular task in runtime, we can do that by using vtask priority set function call. Vtask starts scheduler starts the free RTOS scheduler running in OS mode. Before calling the scheduler, main or a function called by main will be executing on user mode or application mode. Calling a scheduler, we provide a supervisory control (SVC) to our application. Inter-process communication and synchronization. The inter-task communication service of the kernel allows tasks to pass information to one another without the risk of damaging the information. Without inter-task communication and synchronization, tasks can pass corrupted information and interfere with each other's operation. IPC queues provide a task-to-task, task-to-interrupt, and interrupt-to-task communication mechanism. Queues are used as FIFO buffers. When we call the create queue function, the kernel will create a queue for us. Then with the exposed API we can communicate between two tasks and pass information. Ipc Mailbox. Mailbox is also an inter-process mechanism same as queue, the only difference is Mailbox has unit size. We can create a mailbox by calling the queue create function and passing one. Here the transfer of message is done one by one, unlike queue where we can pass number of messages at a time. According to application, we will choose between queue and mailbox. Ipc semaphores are used to synchronize two or more tasks. If there are a number of resources and number of tasks running and using those resources, then a semaphore can be used to synchronize them. Semaphores can also be used as an inter-process communication. Mutex is basically binary semaphore, which means one task can own a mutex at a time. The main difference between a binary semaphore and a mutex is in binary semaphore one task can give the semaphore, whereas the other can take the semaphore, but in mutex the task who takes the mutex should give the mutex back. Real-time embedded systems has to take action in response to events. Event groups allow a task to wait in blocked state for a combination of one or more events to occur. An event group is a set of event flags. Event flags are arranged in a group of 32, means event group variables are 32 bits. There are exposed API function calls to create, set, delete event group. The TCP/IP stack is an example of use of event group. A TCP socket must respond to many different events. As we have already discussed that embedded real-time systems are event-specific systems, so other than event groups, one more way of generating and handling an event is using interrupts. Interrupt is a hardware or software-generated signal that halts the processor and tells it to run a specific code from memory. That special code is called Interrupt Service Routine, ISR. Interrupts can have priority same as tasks, but tasks will only run when there are no ISRs running. In other words, lowest priority interrupt can preempt a highest priority task. Interrupt latency is the time taken starting from interrupt signal to be generated to execution of the first instruction of the ISR. And the time taken by the ISR to finish execution is called interrupt delay or ISR processing time. Priority inversion problem happens when a high priority task waits for a resource which is held by a low priority task which is running, and a middle priority task which does not need that resource comes and preempts the low priority task. So the high priority task will be waiting for a very long time. The solutions for that are priority ceiling. With priority ceilings, the shared mutex process that runs the operating system code has a characteristic high priority of its own, which is assigned to the task locking the mutex. This works well, provided the other high priority tasks that tries to access the mutex does not have a priority higher than the ceiling priority. Priority inheritance. Whenever a high priority task has to wait for some resource shared with an executing low priority task, the low priority task is temporarily assigned the priority of the highest waiting priority task for the duration of its own use of the shared resource, thus keeping medium priority tasks from preempting the originally low priority task, and thereby affecting the waiting high priority task as well. Once the resource is released, the low priority task continues at its original priority level. A deadlock is a situation where tasks are blocked and are unable to run. Deadlock can occur due to certain conditions. If tasks are mutually excluded, that means they are using mutex or any kind of locking mechanism. If tasks are holding a resource and is waiting for another resource to be freed. When tasks are non-preemptible. Cases where tasks have similar priority and one task cannot preempt the other. Circular waiting. It is similar to hold and wait, where multiple tasks are holding resources and are waiting for each other's resources. Now what to do if a deadlock occurs? There are certain ways to resolve or avoid deadlock. If a deadlock already occurred, we can use ostrich method or force preemption method to get out of the deadlock. Or we can use Banker's algorithm to predict a deadlock situation beforehand or find a safe sequence of tasks to avoid a deadlock altogether.